Hi all, how are you doing? How is it today? Uh, let's just double check the connection and the stream. Is it healthy? Is it okay? And then we'll be right on time. Please say if the connection is okay, if the stream is going, and do you see the picture? I can read your chat right here. So we have several attendees today. Ivan Boldyryov, Alastair Leith. Sorry if I'm pronouncing incorrectly, you can correct me. And Apollo. Apollo asks, what do I think about FP in modern C++? Yeah, all right. Alastair says he can see. Just to be clear, this talk was specifically dedicated to present monads to Alastair because we were talking about that in Twitter, and I thought it will be useful to present some knowledge and maybe some another approach to learn monads will be useful, will click for you. I hope maybe not, because monads are not an easy topic. It's definitely not an easy topic. I personally had some troubles with monads like maybe 6 months after I started working with Haskell, started learning it. Yeah, and a complete understanding of monads came probably maybe 1 year later, something like that. And I needed an intensive practice with different monads to see that they all have something in common, and different monads can be really used in the same way, and that's an important idea. Another idea is that we don't really need to know what a monad is. We only need to know how to work with that. That will be two main points. But first, let me answer the question by Apollo. What do I think about FP in modern C++? I think modern C++ is a language we deserve. Like we are too sinful on this earth, and C++ is our punishment. So we could all get to heaven after our C++ practice. Modern C++ is absolutely mind-blowing language, and it has so much complexity built into it. Also, yes, functional programming ranges came to C++. Template functional metaprogramming was there all the time, and concepts from Haskell like type classes mostly, and more other features, they certainly make C++ even more difficult. What do I think? I'm not sure uh, if this all is popular in the practice in the industry. I'm not sure, because I don't work with C++ anymore, and I hope I won't be working with it. But yeah, it's nice that C++ has those features now, but mm, it's very difficult to learn this language because you don't know what is needed, and every code base is vastly different from every other code base. So yeah, but all right. So let's talk about monads. Yeah, you can ask questions in chat. You can request some topics if you want to. But monads, mm, what are monads? As I said, the question "what is a monad" is a scientific question. I would say it's a math question. It's not a question we as developers should bother, because what is a integral? Integral is some mathematical structure, but how you can use calculi to calculate, for example, flows, that's another story. You don't define integrals. You use some tricks to integral to make integration over some data. You don't really think about proofs and theorems. You just use it as a tool. Same is for monads, and as a tool they are not that difficult. But first let me briefly say about my books. In functional design and architecture I am giving some introduction into monads from the practical point of view, especially into state monad, into free monad, into IO monad. And there is no academic jargon there that is related to the monads. And so I'm describing how to use them in a real code bases. This is the approach I would be happy to have in monad tutorials, but most of them are talking about the internals of monads, and those internals may be too mind-blowing to start from them. The same situation with lambda calculus and functional programming. You actually don't need to learn lambda calculus at all. You don't need to know it to do functional programming in any language. And don't listen folks who says you need to know lambda calculus or even category theory. Don't listen to them. That's just an attempt to bring you into their the world they love, but it's not really necessary. So this is what Haskell monad is, and please forget about those two things, because we don't need functors, we don't need applicative, we just need to work with monad, and we don't need to roll out monads the correct way in other languages. Everything can be done with the only bind function that is essential to monads. Every monad has its own bind function that does some things, and we will try to stay away from those internal things from category theory, but maybe not directly from category theory, because this is another topic. We are not scientists, we are developers. Alastair says, I actually learned simple lambda calculus for fun. Sure, learning for fun or even for some deal, it's up to you, absolutely. You can learn whatever you want. I'm talking about the way to get some intuition how to deal with this stuff. And all the functions, all the monads have some one idea in common. When you write a monadic code, like in the middle, you always have several monadic functions to call, and those monadic functions look like they're organized into chain. You call one function, you call another function, you call a third function, you get the result, and this is your monadic code. Then you need to unpack the result, because a monadic function returns a monadic result. And most of the monads have this idea of running. There is a regular code, and to enter the monadic code you need to run a monad. You need to run your sequence of your monadic functions. Let's call this sequence scenario. I prefer to call monadic code scenarios. This is the code we see in our editor. It's the code we write, but actually every monad has some shenanigans behind the scenes. It does something for you while evaluating your actual code. Your monadic function can do whatever your business domain requires to do, but behind the scenes something else happens. This else, what happens, it depends from monad. Every monad has some idea what auxiliary functionality it will be doing for you in the background. For example, for state monad, it will carry state in the background. For maybe monad, it will carry the absent result. For error monads like IDA, it will carry errors in the background and will process them correctly. And you don't need to know about the internals. You only need to know how the actual flow of monadic code works. So what? Something is in the chat. Or in my case, wannabe developers, says Alastair. That's okay. It helps to understand the associative syntax of Haskell, which is very different to most programming languages. Alright. Yeah. Lambda calculus can be useful, but I'm not an expert in lambda calculus at all. I had some courses about lambda calculus in my university, and I'm in Haskell for more than 10 years. Still, I don't know lambda calculus or even category theory. That's not my area of interest. As I said, all monads have some idea in common, and if we take a look at the bind function for each monad, we can notice the bind function has some pattern, follows some pattern. The bind function is not an easy one for sure, because it takes two arguments. For example, this one bind function for maybes takes two arguments. First, it's a maybe type. Second, it's some function that transforms A to another maybe type. And finally, the bind function should also return the maybe type. Every monad has to be some type for which there are extra inner workings behind the scenes. And we recognize a monad by looking at what type a function returns. If a function returns something from this list, it's a monadic function. There are even more monadic functions, and there are more monads out there. And I decided to skip them from here. But once you see these types, you can immediately think about those types. Oh, there is, by the way, a typo about those types as monadic functions. I mean, function plus what it returns. So everything you know about one monad can be transferred into another monad in terms of usage. This is the idea to keep in your mind. You don't need to understand what's happening here. It's just an example, because we would like to approach the task step by step. And if I have been talking about C++, then I would show you this slide with kind of monads. In C++, you also can implement them. And there are two monadic types, expected and optional, that repeat and reconstruct what Haskell has for either. This is either, and this is maybe. So even C++ has monads, but this is not the only way, only place in C++ when you can see monads. I'll tell you about metaprogramming in C++ shortly in the end, because template metaprogramming in C++ is a pure functional programming, and in this pure functional programming you don't have exceptions. You can construct types over types. It's all about type level programming, but there are no exceptions. And if you want some safe calculations on this type level, monads emerge naturally because they help you uh, to process errors. Same can be said for const expr subpart of C++. It's also some kind of functional programming, and it also has um, uh, this property. Uh, you don't, you cannot throw exceptions from it. Well, my knowledge of C++ is rusted, so I can mistaken here. So, but anyway, even in concept, you can do a monadic binding for calculations because it's a pure context, and there is no other way to process errors. Well, technically, I believe there are many ways to process errors, but monadic error processing is another viable option. So monads can be used in other languages too. That's too early because it's slow. Hmm. Hmm. I'm back. All right. It's the second time when my OBS crashed on my machine, so this can happen. This can happen. I hope I'll notice. All right. I hope everything is fine and we're back. Let's talk about uh, monads in Haskell because C++ is a difficult language and we don't really want to learn monads in C++. Let me first write some initial code. I actually have a predefined code behind the scenes. I can copy paste, but we probably want to recreate it ourselves. So we certainly start from the simplest monad possible. It's the maybe monad, and I'll show you what's the idea. Well, first we need some task to work on, and this task will require maybe processing of maybes. Let us have a user. It's a classic example actually, and why not follow it? We have a user with data login and possibly person. Possibly because we can really ask a user without um, asking him to provide the data. So users can be anonymous, maybe person. And person, let it be person. My typing skills are not very great, I would say. And person will be p first name, p second name, and second name, last name, and ph. And also h can be absent, so a person doesn't have to specify theirs age. Well, that's our task, that's our domain. And we also have some database. Import qualified data map as map users database map. This map will keep users by their logins, so it's essentially a dictionary from strings to users, from logins to users. From this moment we can see that not everything is defined, right? Some data can be absent, and we might want to work with this data uniformly. Well, the naive approach will be like that. For example, we want to get person name. It's a simple function, person, and returns name. This is a simple function because it works with person, and we have everything here. P first name, P last name, for example, right? Now we can work with user. What if we have a user and we want a person name? That's a problem because the person can be absent. Get, for example, get user person. That's only example. User, and the person may absent, so be the name, right? And this is why we need to denote that the data can be absent. Normally we just do the same. User, normally we just do the following. We ask for internals of this user and pattern match over the internals. Case you person user of just person. All right, we are fine. There is a person, and we need to return just yeah right. Just get person name person. If we don't have it, then we will get nothing, and we only can return nothing to indicate that there is no data. This is the environment we are working with. That's our unfortunate situation, that some data can be absent, and we would like to avoid writing those case constructions. For now we don't know how. We can only do it the naive way. Let's, for example, let me copy paste some code to avoid writing too much. Some code, I mean database, and some get functions. And let's examine this code. So we can request person name, we can request person age, but the age may absent, so maybe int indicates that, and we return the field that is maybe age, maybe int. We can get a person from user, and again the person can absent, so maybe person, maybe yes, maybe no, right? Like in a song. Get user, we can get user from the users database, and again it can be absent because we can request some data that is not in this list. So once it can be absent, we again return maybe user, maybe nothing, depends on what you requested. This is a very plain code, and we can try something. Print get user, for example, Bob. Let's just Bob from users. Let's just run it. No instance. Okay, this is a small addition to the data types to be able to print them to console. Now I called the function, and we got the result, right? The result is just. because we have some Bob in this list, in this map. And let me show you the maybe data type right now. It's just maybe a is just some value or nothing at all. This is a very simple data type. We indicate the absent data by wrapping some user data type or person data type into it. And for now, there is no yet any monadic code here. Only bare function applications, nothing more. I just request stuff directly from there. Alastair Leith asks, what does the type users map user line do again? This is only a type alias. Users is our new type that will be meaning this. We have a map. It's a dictionary. It's a dictionary, I mean collection of some data in this form. Key, string, and value is user. So this is our key. This is our value. It's a key value collection. And we put several things into that. Users. Our users is at the database, handwritten, and we have 3 records in it. If we request some absent data from this database, well, yes, yeah, maybe it exists there. If we request something absent, we will get nothing. Yeah, just as expected. Now we would like to write some business logic for persons and for users, and this is where the things starting being complicated. Let me get my hint. Yeah, describe person. Let's, for example, write a function that gets a user from the database, gets a person from the user if the user exists, and describes this person in some way. Describe person, we get some login, and let's just keep it simple. This function should return description. This is key, I mean login, and this is description. First, we need to ensure that we have this user, right? Case get user login users. We request this user from this login from users. Okay. If nothing, what should we return? Describe person function says it should return string, but we can certainly return there is no such login. We can. But the code below, for example, right here, it doesn't know that some error is returned. It can just print describe person and it thinks there will be some valid description. It doesn't expect the string of with error, because who knows, maybe it's a description, right? Maybe there is some person with such strange name. How can we distinguish between these two situations? Well, let's put it simply. First of all, we can just throw an error and do not bother about this absent case. Bam! the program has crashed because we got an error. Let's keep it like this for a while. This will be an error. But once we have something, just person, we finally can form a real description. And what we want to return? We want to return first name plus last name, and if the age is specified, then the age too. By the way, not person, it's user. It's user. We are too fast. It's because it's the user's database, right? We are getting a user. So we first need to ensure that the user contains the person. Case get person user of, again, it can be nothing. Get person, we have function just returns the person of the user, and we can get nothing. Again, error, the person is not specified for user. Like this. Let me put it like that. And person, we are fine. Finally we have a person, and we can certainly return some string formed from person. There is first name, there is last name. Let's do that. P first name person plus some space plus P last name person. This will work, yes? Let's type Bob. Yes, this works. But we have we also have a age field, but and we want to include this age if it's specified, right? Again, we need to ensure it's specified doing pattern matching. Case what is the accessor? PH, right? PH person of nothing. If nothing, alright, return the string without the age. But if there is one, we want to return the same plus age. The space and converting integer into string. Yeah, it works now. So this is our naive approach. The maybe type is very convenient, right? We can really do a lot of stuff using this type. It's convenient because it's simple and easy to pattern match over. But look, it's a lot of strings here, a lot of code. And also this error here and here. We don't really want errors in exceptions in functional code. We want something more rigorous because our functions should be pure, they should be reliable, they should be easy to work with. The description of this function doesn't tell us that there will be some exception on an error case. It's not a good situation actually. Our code should be obvious from reading the least possible information. We could fix it a little bit by saying, alright, maybe we need to return maybe string instead of throwing errors. Why not return nothing? Here, let's comment out the error. Let's return nothing here. And here we should return maybes, right? Not strings anymore. We can say, alright, it's our result, just wrap it into the just type. And now our function is completely defined, is very clear, is pure, and do not throw exceptions. If we specify something wrong, we get nothing. We don't know the error, right? We don't know what's happening there. Maybe the user was absent, maybe the person was absent. For now, let's put it like this and do not think about errors. Not something happened, something bad happened. We don't bother about that. We just want the description when everything is fine. Let's call Alice, for example. But monadic, we actually wrote a monadic code. It's a monad that works like gets some maybe result, then checks its contents, then decides on what to do next, and again checks some maybe result, and again checks some maybe result. In Haskell, it's too much code. We can write the same, and this is where the power of monads comes from. We can write the same using the do notation. See this, right? It's a monadic function. Yeah. Yeah. OBS is crashing on my Linux machine, which is not good. I need to fix that. But anyway, describe person один is a describe person one is a monadic function that takes a login and returns maybe string. And we can convert the whole code into simple strings. Do. There is a do notation that represents monadic calculations. Once you see the do block, you need to verify what is the returning type of this function, and this do block will be of this monad. So right now it's of the maybe monad. What is the get user function again? Let's double check. We see again it's a maybe function, the function that returns some maybe result. So it's a monadic function actually. This is how we recognize it. And this one is also monadic in the same monad. Get person, same story. Monadic because it has maybe person as the result. Get user, also monadic function. So essentially this means we can use those functions in the do block without doing what the monad does. The monad does what we see here. It pattern matches over some monadic values and either returns nothing or proceeds with the evaluation. So the whole code will become the following. Get user. This is a call of our monadic function. The result should be put into the user variable. In here happens this pattern matching behind the scenes, and now we have this variable here. User is this one variable. So we can do the following, the same for the following function, and we can get person. If any of those calls return nothing, nothing will be propagated back to the described person, because the chain will be kind of terminated on this step, and nothing nothing from the next lines will be evaluated. In here we have some another problem. because now we need to make a choice depending on what ph contains. It can contain something or nothing. We actually don't have to wrap all the calls into monadic chains. We can do same thing as we did before. It's allowed to pattern match. Yeah, ph is also, yeah, ph is also a monadic function. I need to show it here, but we are allowed to pattern match over monadic values here, right? And we just need to return something in the end. Something in the end means maybe. This time it's just this value or just that value. I essentially did the same. Let me put the ph. Yeah, ph is the accessor, that a field that returns maybe, and so it's also a monadic function. Ph is a person to maybe int function, also monadic. It's a field accessor for ADTs. So essentially that's it. Nothing mysterious is happening here. It's the same code as above, just with some syntactic sugar that hides those pattern matchings and those case constructions behind the scenes. It hides pattern matching and unwrapping here and here, and finally this is like the same function. We can call it, and should be the same. Yeah, really nothing scary is happening here. But yeah, and this is the simplest possible monadic code. Simple maybe monad is very convenient to get into the monads, but maybe we want something more. Let's make some break, and maybe you can write something into the chat and I'll read it. And then we will solve some problem with our code, meaning it's not much descriptive. We get nothing, but we want to know exactly what went wrong. So can you please tell me if everything is fine? All right, no comments yet. All right, let me show you the either monad, and you will see there are many similarities between maybe and either, and those two examples will show you that monads can be we can work with monads uniformly by knowing what they do but not how they do. So how would we solve the problem? We want to return either error if something went wrong, or a valid result if some is when everything is fine. We can use the either type. This either type will have two type arguments, one for error and one for a valid result. One value constructor will return error, another value constructor will return a valid result. This is the either type, and it's very simple, and actually maybe is a weaker form of this type, because we can remove the e from here and it will become maybe. up to the identifiers. Just rename either to maybe, left to just, left to nothing, right to just, and you will get maybe. But we want to pass some value, some error value from our functions. This means we need to update the described person. Either. And now we need to probably update all the functions from here. For example, get person age. Either. It's maybe age. Now we need to pattern match. Case mb age of nothing, because the type of this field hasn't changed, didn't change, so we still need to pattern match. But on nothing we return error. Age is not specified. On just age we return age. That's it. What about the get person? Let's do the same. Mb person of nothing. Person is not specified. Otherwise we need to return the person. Maybe either. And here we have a get user. It's the map lookup function that searches for the login. It also returns maybe. Reconnection. Yeah, reconnection. Good. We're good. Some disconnect happened. Nothing. Left. Let's do the following. Left. User not found. And let's communicate what user is not found. But when it's found, just user. Right, user. And again we need to change either. Now our functions have more power. They can communicate what went wrong, right? And how would we work with that? Everything else here stays the same, because we didn't change the types themselves. We only changed the access functions that work with data. Oh, sorry, I missed the type, because we want to return string as a error, and I need to specify what error type should be here. It should be a string. We return strings as errors. So this is an error, this is a return type. This code will stop working for sure. The string as this string is a error, and this string is a result. We can actually make type aliases error to make it more clear, like this, error, and maybe here error. This will be more clear, right? And now we have the same problem. The get user returns either. We can pattern match over it. Left error, so just return the error. Right user, again left error. Maybe we need to specify error 1, error 2. Left error 2 and error 1. Right person. This one returns maybe, so we need to pattern match. But here, right Right. Correct. This is a correct result. Let's comment this out and just see what happens, and maybe we made some mistake. No mistakes. We just changed the maybe to either, and now we can see the problems. For example, DDD. User not found, DDD. Alright, there is an incognito user there. Person is not specified. Let's double check. There is incognito. The user is there, but the person is not specified indeed. Now we got some more powerful code that is that can communicate problems, but working with it is yet not very convenient, right? The same problem, absolutely the same problem, and it can be solved with the same trick, with the same solution, because either is another monadic type. This time we need to change it a little bit. Either error string, and now look, get user returns either now, and the code stays the same, because in here we will get the same pattern matching as above, and we don't need to change it. It works the same as maybe behind the scenes, so it will look exactly the same. Get person, no change. PH person, yes, we need to change it a little bit, not here because PH returns maybe, but here. Right. And voila, again, it's our monadic code, nothing scary. We can ensure it works like that. Person is not specified. That works. Alastair Leith said, I followed that pretty well. Makes sense. Yeah, good. So we can see the types. Let's examine the types, right? Either error user, either error person, either error user. This is still maybe. It's monadic in a different monad. But now either says that the do block should be in the either monad. We cannot do the following. For example, ph person. We hope that monadic maybe value will be unpacked here, but unfortunately it won't, because the do block is only for the either right now. That's not possible. You cannot merge two monads like that. So this is wrong. And look, the IO type is also a monadic type. This is why we can actually use the same do block here, and all the IO returning functions will work in this do block. For example, the print function is an IO function that returns nothing because we don't expect any result from the print. We expect results from maybe functions and from either functions, but IO functions can do some stuff and then nothing else is needed. There are other functions, for example, get line. It asks a line from a user and it returns string. As long as an euro IO as long as look my tongue is getLine is a IO function, right? And it returns a string. So this means we can unpack the result of this function. Line, get line. It doesn't take any arguments here. It takes arguments to print, and this doesn't take any arguments. It just says I am monadic in the IO monad, and when you unpack me, you will get line. And I can call path strlen line, or maybe like this. You entered, or maybe like this, line. And podstrlen is a monadic function that takes a string and again works in the IO and doesn't return anything useful. Let's try it. This is the online compiler, so it doesn't know what I want to type from the console because there is no console. I'm not sure, maybe I can specify some results into the console when I run it. I don't know how to do this in this online compiler, but in here, in a normal program, the user will be asked for entering some line, some text, and the text will be printed here. That's actually it. You see, three IO functions all go like a chain, and something happens behind the scenes. For every monad, it's true that something happens there. In our case, the IO does some real world transformations behind the scenes, and we don't see it here. But actually, there are internal data types that are being passed here, from here to here, from here to here. We don't need to think about that. We just want to know how to work with the IO monad. We cannot put monadic, maybe monadic functions from and either monadic functions like this into here. We cannot unwrap it. For example, describe person BBB. This will not work because describe person is another monad, right? Yeah, couldn't match either with IO. We already specified the monad, but we can put the same value into variable with the let syntax in Haskell, and the desker will be of type either error string, because we called this function. We don't do any unpacking here. We can actually case desker of right. Let's rename it. desker right desker print desker, or left error print error. We can do that because the case block will now be of the IO monad. Those two results of this case block will be IO functions. So we are in our right to pattern match over some results. Like that. Bogdan writes, hi, thanks to you and some other folks from Scala I discovered and then learned FP in Haskell Scala. Yeah, good. So I demonstrated the only one simple idea, and this pattern will persist for all the monads. Let's try to take a look at C++, because why not? I wanted to show you this code. it's a C++ code, not complete one, but anyway, imagine there is a code that cannot return, cannot throw exceptions, but still needs to evaluate integer multiplications and divisions and other calculations in a pure way. So there are several exceptions that might be thrown in a normal calculation code. For example, division by zero, or maybe some other errors. And in here, we are not allowed to throw exceptions, but we can use the idea of monadic either to make a code that either returns a good result or returns an error, and then the caller will decide what result it gets. If it's a good result, okay, just continue working. If it's an error result, maybe do something with that. So in C++, there are areas of the language in which this monadic either or maybe processing is very convenient and important. It's important to the extent that in C++ we have actually special types for that, and we can, yeah, we have optional, which is an analog of maybe, and we also have expected, which is an analog of either. Let's maybe try to do the same. I won't be typing the code myself because it's slow, but let me just go through the example. I don't use optional or expected here. I created my own maybe structure to make it more similar to the Haskell code. This maybe structure, we don't have algebraic data types, right? We cannot have just and nothing variants for the same type. Instead, I say if this shared pointer is null, then it's nothing. If it's filled, then it's something. All right, this is our convention for the maybe type here. Also, we have a person. It works exactly the same as in Haskell. There are two fields of string and there is one field of maybe int. There is a user, again login, and maybe a person, maybe defined, maybe not. And there is a user database, logins as a keys and user as a content. And also there are get functions. We, for example, can request for person name, first name plus last name, or we can request for a person age. And yes, we see this maybe. This function returns maybe. This means this function actually is monadic if we only had the monadic code behind these things, but we don't actually. There is no special code for maybe in C++. It's my custom type. I need to write that special code. I need to write the bind function for maybe. Let's first see if this works even. Warning. No return statement in function returning known void. There is a lot of code here, right? And there is some error here. Yeah, that's return result. I need to fix that. Let's all right. Never mind. It's not the code I wanted to demonstrate. 1 second, please. 1 second, please. We were here, right? We were here. Describe person 1. Absent. This function is absent. In C++, we don't have the do notation. So every monadic code we will write here will be very boilerplatey. It will be very heavy, but we'll try. First, we need a mechanism to bind monadic functions. We don't see this mechanism here because it's hidden, right? But we see this mechanism here, so we can roll it by ourselves. Essentially, what I want to achieve, for example, we have a get person with some user, get person, yeah, and some user. No, let's not do get person, but get user from the database. Yeah, we need this function. Maybe user, get user, const string login, and I need to request the container from here, right? Const users. Let me just copy paste the contents of this function because I really don't remember this C++ anymore. So we first ask the user containers, the user's container, to find some login. If the iterator reaches end, then there is no such user presented, and we want to return nothing. If it reaches end, then we return nothing. This will be the equivalent of nothing in C++, and this will be the equivalent of just some result. Yes, it's very heavy because I need to create maybe structure, and I need to create a shared pointer to the internal data, the data I got from the container. Yes, this is very boilerplate, very wordy, but it is what it is. Now what do I want? I want to get user, for example Bob, and I want somehow to pass it to another function, get person, and I want somehow to pass the result of this get person into the final function, get person name. This is actually a monadic chain, and we need to figure out how to make it working, because what means we call user and then pass what do we pass here? Again, we just follow the same pattern as we did before. We can do it here. Doesn't matter. Auto result get user Bob from users, right? Users, I need users. This will be result of type maybe user. I can do the following. Maybe person get person result mb user and actually this is a problem because that our get person function doesn't accept mb user. It accepts just user, right? Get person accepts just user, so we cannot pass maybe user there. We need to unpack it. We need to do this monadic unpacking manually. How we can do that? Let's write a special function for that, the bind function. It will be a template function. Template type name a, type name b. It will have two type variables. Yeah, maybe b. It will return the result in form of maybe of the second type. It will take the a type as an input and the b type no const maybe a ma, and it will take a function, a special function that will be doing some unwrapping. This is where we're doing some functional programming. Const function b, maybe b. I'll explain it. Let me write it first, because explaining and writing simultaneously is difficult. F. So essentially this function is of type bind maybe a, some function from a to maybe b to maybe b. Is the same bind function that works for every monad. Let me return to this. For either it will be this function, for maybe it will be this function, for IOB it will be this function. And these bind functions work behind the scenes. They do monadic binding for us. The maybe bind does only this. We can write it first in Haskell, for example. Custom maybe bind maybe a to maybe b, maybe b. If it's nothing, then and there is some function, we ignore the function and return nothing. Or maybe I should not pattern much over the arguments and do case switch to make it closer to this, right? Let's rewrite mba f case mba of nothing return nothing, just some value. We need to apply function to it. That's actually everything the bind does for maybe. For either it does the same, except maybe either what I'm writing, either and either case a. Let's rename it. Right left error returns error. Write some value we need to apply the f to that value, and this f will return this ida, and it will go here. So it does pattern matching. We essentially extracted this pattern from here to here, and it will work behind the scenes. We now use this bind function to connect get user to get person to ph. As the same thing happens here, we just don't see it. There is a stock bind function. It works pretty much the same and does this binding behind the scenes, does this pattern matching for you. We can do manually. Let me just show you. For example, get user login like this, Bob users. This is the first argument. Then we need a function lambda user that will be returning some ida, and we need to process it like this. Maybe for example, we can return user right from here. This will work. Or we can continue our monadic chains inside this bind. We can ask for another bind, and we can, for example, get person. Sorry, another. My brains don't work anymore. So we get either, and then we have user, get person user. This will be another either function. We can custom either bind. This returns either, right? So we can put it into the first argument of the nested bind, and we can bind the result to the person. And here we also need to return some either result. For example, write person found. For example, like that. And look, this is a manual chaining of monadic functions with the bind function. All the monads have this mechanism behind the scenes. They all nest functions into another functions with the bind function, with the help of this tricky beast. And for each monad, this bind function does own things. It always unwraps some monadic value in the first argument, and always passes the result to the internal lambda, to the internal function. And this internal function can do the same again, and then again, and again, and again. This code is essentially the same code as here, just with the help of functional constructors. We can now do it with manual pattern matching. We can do it with the do notation, or we can do it functional way with custom monadic binds. Same in C++ actually. We don't have do notation here, and we don't want to wrap and unwrap those types manually. So let's roll up a custom monadic bind. In C++ it will be very horrible. So if mb_val, if it filled, then we need to call f function from we need to call a function, right? F from MA, MB. Well, this is a pointer, so we need to dereference it. But otherwise, we need to return nothing. And nothing in C++ is maybe of type B. We constructed null ptr. That's actually it. The bind function for maybe will work like that. And combining functions with it won't be a pleasure, but we will try. Auto result bind get user returns maybe user, so we can actually bind this MB user to the next lambda MB user, and we need a lambda. In C++, lambda can be done with this syntax: auto user. And here we should return some maybe result. For example, user.login, maybe string, make shared string user login. And voila, we just made a custom monadic binding in C++. You certainly can nest more monadic bindings here. I won't do it right now because it's too tedious and too difficult, but this is how monads can be done in C++. They are not generic, meaning that there is no do notation that would work for everyone, for all the monads, but you can roll your own maybe and either monads and other monads by specifying this bind function and by doing some very ugly but still functional programming with this bind function. And actually there are even more convenient tools for that. Optional for maybe, expected for either. There are monadic methods in those types, and the story of monads in C++ is difficult. You can do that. You essentially can do that. I will probably show you quickly C# link. Yeah, I see some comments. Typo, yes, I fixed the typo. German Danilov. Oh, hi, hello, Alexander, says German. Yeah, hello, German. Nice to see you. And German is my close friend. But let's examine link. Link is a functional way to operate with collections in C#. It looks like SQL but with code. Actually, there are several different syntaxes for link. This one really looks like SQL, but there is one more syntax that looks more like functional programming. Maybe we'll see some examples here. Link queries. This is a SQL-like code. I don't need it. Show me something. Write link queries. That's all. Not what I want. Language, standard query operation, asynchronous, C# concepts, sort data. Maybe somewhere here. Yeah, it looks like this. There is IEnumerable type, and this IEnumerable type contains different methods to work with collections. For example, it can sort collections, it can select data from collections. Actually, it's kind of well, filter operator or something like that. There are even more functions, but what we are interested in is select many. Select many method from not from here. From here, I guess. This is a select many method. Actually, it's a monadic bind. It has a very strange result, very strange type, but it's the same as monadic bind. It gets some queryable t-source, then gets some expression meaning function, and returns some result. How to demonstrate this properly? Maybe with ChatGPT. Hi, please show me an example of select many from link C# and tell me why it's a monadic bind. I don't see anything happens. Come on. All right. Bad luck. Doesn't work. All right, you just can believe me. Link has some monadic behavior inside it. And if you, well, I can tell you more about monads. For example, I can show you how to work with the state monad. Let's remove all the code and talk quickly about the state monad. Import, qualified control monad state as st. State monad mimics mutable state, but actually it's immutable and pure. For example, we can calculate some data factorial stateful. It will be a state monadic code that stores some integer number inside it and returns integer number, and also gets some integer argument. So state monad has two arguments, state type. This is a state and this is return value. Once you have this monadic function, because it indicates it's monadic, you can use do notation the same way. You can consider that there is some hidden environment in this do block, and this hidden environment holds what we pass here, or like integer, or maybe string, or maybe some user. This will be the context, kind of mutable, but not actually. In our case, we are interested in keeping the accumulator there. We can get that data from the state context like this, and we can put new data into the context. Put accumulator multiplied by n, and from this point of the do block the integer value will change in the monadic context. Here it's yet accumulator, and here it's by multiplied by n. So if we get another acc, then we get multiplied. Let's call this function again with n minus 1, and we certainly need a base case 1. Let's just return not just 1, because we cannot return integer. We should return state. In this case, we need to wrap the 1 just bare value into something, and we need to return integer. All right. There is a pure function that works for every monad. Pure. In our case, it will work for state. It takes some value and returns state state A. It returns this value wrapped into this state. So we need to put pure here. We multiply it by n. No. Why do we return pure? When we reach the end, we need to return the internal accumulator actually. So what I need to do is to ask accumulator again and pure acc. This get function has the following type: get state. Put state empty. It takes state. So this get function is monadic one. It takes the context and returns this context as a result. So we can unpack the result here. Put is another monadic function that takes a new state, replaces it here, and returns empty result. We actually can unwrap empty result here. Why not? This doesn't make much sense because there is nothing interesting about parentheses. But we can unwrap this state. We can unwrap it here. We can unwrap it in the main do block for example, print something, and we can unwrap this empty result here because print takes something to print and returns IO with parentheses. So unwrapping empty parentheses is possible, but I don't think it's necessary. The do block essentially allows us to avoid that. Well, actually, that's mostly it about the state monad as it works. Still, we have to run this function. It works in the state monad, but we need to run it somehow. And yeah, st, because it's qualified. Let result st run state. We need to specify what exactly monadic code we want to run. Calculate factorial stateful 10, and we need to specify the initial state for this context. In our case it will be 1. I don't actually remember I should put it as the first argument or the second, or swap them. Let's figure it out. Variable not in scope get. Yeah. st get, st put, because I imported it qualified. Something. So we got something here, and we got some result here, print result. So we have a state itself, and we have a result from the monadic evaluations. The run state returns both. Run state returns context, current context, and result. There is another evaluation function, exec state. And exec run exec state. It will return something. It will either return context or the result. I don't remember which one. We can figure it out by doing the following. Let's the calculations return some value, and let's the contexts have another value. So we figured out that exec state returns the result, the context. And there is also eval state that will return the result. So you can see we used the do block as pretty much as the same as we did it for IDA and maybe, and the same as the IO monad, and nothing scary is happening in front of our A's, but we don't really know how the state monad works. What are the internal bind transformations here? How does it keep the state in this do block? How it passes the state through the chain? It actually doesn't matter, because we are interested in working with monads, not learning them. But if you want to know, you can check out the implementation, and you will see that there is an argument passing state here. This get function, this unwrapping, and etc. The context is being carried with the results all over the chain. The context, there is a context here, and it can change. It will be passed here and will change, and then the context will be passed here and may change, and it will be passed here and also can change. So the state monad has this idea to carry the state behind the scenes. It does it for us. We don't need to do it manually. We don't need to have argument passing state. Yeah, that's pretty it. That's pretty much it. I believe this was at least insightful or maybe useful for you. Let's read the comments. Alexei Luzhin. Hi, Alexei. Glad to see you. FMAMB. Well, maybe I just lost the context already. Maybe. So nothing else in this talk. Yeah, I don't have slides anymore. A few words about function and applicatives. Essentially, the bind function can be done step by step using other blocks. We did it directly. We created some mechanism and embedded it into the bind function itself. But this mechanism can be separated into several parts, and some part will be here in the fmap function, some part will be here in the AP function, and then bind will utilize fmap and AP to do its stuff, but this is not really needed. Both fmap and AP can be expressed through the bind. If you have a bind function with all the mechanisms of monadic binding, those two can be expressed with it, but not pure. Pure is a separate function that wraps some bearer value into your monad. So it comes from applicative in Haskell. In monad there is another function that is known as a return. It does the same thing actually. IFA. They are the same, pure and return, but this is a historical reason that the return function exists. I recommend using pure without noticing the return function. You can still see this function in old code bases, but pure is a better way to do that. Alexey Luzhin writes in C++. Yeah. Alastair writes, it was really good, thanks. Yeah, welcome. C++ was ugly, but it was interesting to see in a language I barely know anything in. Yeah, C++ is very weird language, difficult to write, and very, very wordy, extremely wordy, and super unsafe, really. What else? That's it. So, thank you for your attention, and that's it for today. And yeah, bye. What is the auto command? What is the auto command in C++? Auto, this one. In C++, it means I don't, no, it means please infer the type for me. There is some type for result, and it will be inferred. I can replace maybe for auto here. C++ has some type inference a little bit, as much as C# and Java. There is a little of type inference in C++. And in Haskell, you can really rely on type inference everywhere, almost everywhere. In C++, it's a different story, but sometimes it works. So we can substitute actual types with inferred ones. Great, thanks. Okay, I see, says Alastair. Yeah, welcome. Yeah, that's it, folks. Thank you for listening. Thank you for your comments, and probably see you next time. In a week, maybe. I'll do another talk about something. You can request your topics because it's a lot of things to discuss. And that's it for today. Bye.